Welcome to the AST Training Session 3. Today's training will be for radar techs, storm chasers, and spotters. I will start the training with a few visual aid slides and then continue with a training video with analysis by Skip Talbert. This video can be helpful to all storm team members when a storm is approaching your area. In this video, radar techs can compare radar images to the actual view from the storm chaser. As we will see in this video, tornadoes are not always visible. Radar techs can be very helpful relating information to a storm chaser or any person caught in the storm's path. Storm chasers and spotters, always be aware of your surroundings and plan your escape routes. Tornado right here, and you're going to see the rear flank downdraft. Just going to give you some pictorials before we get the film going here. So we can see here's your RFD here, and here's a secondary area of rotations, which is something to look out for visually or even on radar. And this is what they call a satellite tornado, where it actually revolves around the main tornado or rotates around the main vortex. Back over here, here's where your precipitation is. Here's our clear slot. Usually right in this area, I know they had this as the leading edge core precipitation being wrapped around. This is usually where you'll find your hail in this area right here. But this is out here going around like this. This is your hook, and here is the tornado. All right, next slide. All right, and what we're looking for visually, what you can see from a distance of a supercell. Here's our mesocyclone up here. That's where our rotating thunderstorm is happening. Right here's where all the rotation is happening. Over here, this is the precipitation part of it, rain, and you also have the hail core in this area. Forward flank downdraft, this is warm inflow going into the thunderstorm. And then you have the rear flank downdraft, which is down by the surface here, and it's wrapping back around this way. This is where you get your rotation. And also you're getting your warm inflow from this area. You will see here, this is the tail cloud, but usually by the precipitation you can see it follow the tail cloud into the main part of the thunderstorm right here. And also you have your warm flow, where it'll start wrapping around and come down with the rear flank downdraft. And of course there's the wall cloud, and normally your tornado would be right in this area, right around there, right in this area. I like putting this pic in here because you can actually see what wind shear, how it affects the thunderstorm. And right here you're getting the increasing wind shear pushes the updraft tower over. So now if you remember seeing these towers going in the air, and now we have the wind shear pushing it over, and this is where we come up with the mesocyclone right now, where we're getting the rotation. And up here we're getting the updraft. This is more like inflow right here, updraft base right here, and very little precipitation over under the clear slot right here. This is where all your precipitation is right now, and hail would be here. But over here, this is where you would start seeing the hook and possibly a tornado event right in this area. All right, this is a basic illustration of a thunderstorm. And here at the surface, we're showing where we're starting our rotation. And then with getting into the updraft right here, it starts lifting up the rotation. And we have a rotation up at the base right here. which usually right in that area is where we're going to see a vortex form. So there's your updraft going up and going out to the forward flank of the thunderstorm. Over here we got directional shear, and in our illustration right here, this represents here the first line, the winds at the surface out of the southeast with warm moist air. And our next level right here, around 850 millibars, winds out of the south with moist Gulf air. And then winds out of the southwest, and we start getting to the mid-levels right here, right around the 500 millibar. We have winds out of the west at mid-level with dry air. Then in the upper levels, we have winds out of the northwest with cold air. And that's how we get directional shear. That will form a thunderstorm, or possibly a tornado. Then we have the illustration here, silver lining storm chasing tour van. This is what we are going to basically focus on at the very beginning of the video that we're about to watch, and hope that it can help us all out in safety. Now we will continue to the video.
On May 28, 2019, a supercell tracked near the Lawrence, Kansas area, spinning up tornadoes including a mile-wide EF4.
Now.
Among the 21 people injured by these tornadoes was a group of storm chasers. We'll take a look at what happened here, what went wrong, and I'll make some recommendations on how chasers can hopefully avoid such incidents on future events. On the afternoon of May 28th, a warm front and cold front triple point tracked near Topeka. The atmosphere southeast of the triple point was extremely unstable, with Cape values exceeding 4,000 joules per kilogram. With effective shear of 50 knots and enhanced directional wind shear along the warm front, draped from near Topeka to Kansas City, National Weather Service forecasters noted the possibility of strong to violent tornadoes in morning outlooks. At 1:55 p.m., a tornado watch was issued. Storms erupted along the cold front, with a large high precipitation supercell becoming dominant. The supercell produced 2 long track and significant tornadoes in Kansas. The tracks shown here are reconstructed from damage surveys conducted by the National Weather Service, with timings interpolated between sightings made by chasers and Doppler radar velocity. We'll stick with the Topeka WSR 88D radar, as it was a bit closer than the Kansas City Weather Service radar and gives us a good look at the tornado that impacted storm chasers. Please keep in mind that this radar is more than 40 miles from where these tornadoes occurred and is scanning the storm several thousand feet above the ground. Some detail is lost at this range. However, the high-resolution Level 2 data does still provide a good fix on these tornadoes. The motion of the parent supercell has been subtracted from the inbound and outbound wind velocities, allowing for a much better view of the rotation in this storm. A velocity couplet is associated with the tornado southwest of Lone Star, Kansas, followed by a much larger and much more intense area of rotation associated with a second tornado south and east of Lawrence, Kansas. The first tornado formed 2 miles south of Overbrook, Kansas, and tracked approximately 11 miles northeast to Lone Star Lake. The following tornado formed over Lone Star Lake and tracked approximately 29 miles northeast to Bonner Springs, Kansas. This second tornado was a mile-wide wedge that inflicted a single instance of EF4 damage near Linwood, Kansas. In the days following the event, damage surveys and radar analysis identified that the tornado that injured storm chasers was the Lone Star, Kansas tornado. This tornado was fairly long track, inflicted a single instance of EF2 damage near the impact site, and was a main tornado pendant to the storm's mesocyclone. We'll take a look at each tornado track in greater detail, but this loop provides a regional view of where this storm and its tornadoes occurred. Among those impacted by these tornadoes was a commercial storm chasing tour. 2 of the 4 vans operated by Silver Lining Tours that day were thrown from the road by a tornado and rolled into a field. 12 members of the group were transported to area hospitals, with various injuries as serious as a broken neck. This tour is led by exceptionally experienced and highly regarded storm chasers. Figuring out how such an accident could happen and what we can do to prevent future tragedies is the primary motivation of this presentation. A few disclaimers and important notes are necessary here. Storm chasing has some inherent danger. Chasing is a relatively safe activity when compared to many extreme sports if storm chasers are dedicated to educating themselves and following established safety practices. Through the sharing of combined experience, chasers have identified the greatest threats to safety, risk-taking behavior that is wholly unnecessary to accomplishing the goals of storm chasing, and how to best minimize risk. This presentation is done in the cooperative spirit of sharing what we've learned in order to promote chaser safety and minimize risk. The practice of storm chasing is totally unregulated. There is no formal storm chaser training or any official licensing or certification. In this sense, all storm chasers are effectively amateurs. National Weather Service spotter training or formal education in meteorology does not make you a well-prepared storm chaser and is not adequate on its own for safe and effective storm chasing. Aspiring storm chasers and those who are joining a chase as passengers should be made aware of this. Likewise, the information in this presentation is not officially sanctioned in any capacity. It's up to us amateurs to figure out what we're doing out there. I'm going to try to keep this as objective as possible and cite official sources such as event information published by the National Weather Service wherever possible. But the recommendations and conclusions expressed here are my own. They do not necessarily reflect the views of those impacted by this storm. The staff at Silver Lining Tours has elected not to contribute to this presentation. Fortunately, several of their tour clients have generously provided information, photos, and video. Much additional information and video was also provided by other chasers on this storm. We'll take a closer look now at Silver Lining Tours' positioning relative to the storm and tornadoes. The animation of SLT's position is interpolated using information courtesy SLT clients and from sightings by other nearby chasers. SLT's 4 vans drove east through the town of Overbrook, Kansas on Highway 56 as the storm approached, and then stopped 2 miles east of town. The group held here watching the storm for several minutes before continuing east to stay ahead of the storm. A tornado developed within the rear flank core of the supercell. However, the tornado was not visible to the SLT group. SLT took the first available paved crossroad and proceeded north, likely hoping to gain a view of the storm or any possible tornado from the northeast. The maneuver was reversed or aborted, and SLT attempted to return south to Highway 56 before they were impacted by a tornado. The larger Lawrence EF4 formed several minutes later. The storm relative velocity gives a good indication of SLT's position relative to the radar indicated rotation in this storm. Broad rotation associated with the parent mesocyclone of the Lone Star EF2 tornado is initially visible, followed by a tighter velocity couplet associated with the tornado itself. These animations provide a quick overview of how the chase unfolded. Next, we'll go step by step in an attempt to better understand what happened here. After driving east through Overbrook on Highway 56, SLT stopped atop a hill 2 miles east of town and observed the storm for several minutes. Reflectivity at the time showed an extremely large high precipitation supercell to the west, with a V-shaped forward flank extending north of the highway and a heavily rain-wrapped rear flank south of the highway. The storm had been warned for tornadoes, with National Weather Service forecasters citing radar-indicated rotation. Radar velocity at this time showed a broad area of rotation associated with the storm's mesocyclone, approximately 7 to 8 miles southwest of the SLT group. Silver Lining Tours client Jeff Lieberman provided a photograph of the supercell and its structure while the group was stopped east of Overbrook. The details of what's happening under the storm's base are not visible here due to the distance and low contrast nature of this high precipitation supercell. Looking west-southwest, however, some prominent structure is apparent, a long tail cloud marking inflow feeding into the supercell's updraft tower. Even when poor contrast prevents the spotting of other structure, the tail cloud can basically point the way to the mesocyclone and the area most likely to contain a tornado. Indeed, this is the part of the storm that produced a tornado several minutes later. At approximately 5:49 p.m., a tornado developed within the rear flank core of the supercell, about 4 miles southwest of SLT as they drove east to stay ahead of the storm. Initial motion of the tornado was to the northeast at about 35 miles per hour. At 5:55 p.m., the tornado crossed Highway 56, behind the SLT group. Storm chaser James Wilson was driving east through the rear flank core of the storm, his position and viewing angle noted here by the blue arrow. Looking east, his view at the time shows a strong northwest wind. Tornadoes embedded in high precipitation supercells can look like little more than wind and rain without much of an apparent funnel. The wind shifted from west to south-southwest as the circulation crossed the road ahead. Noting a broad yet intense circulation, Wilson reported a tornado to the National Weather Service via spotter network a few minutes later. If SLT received this report, they likely would not have gotten it with enough time to act upon its information. I'd like to thank all of the storm chasers that contributed materials, without which this presentation wouldn't be possible. However, it needs to be stated that many of the videos shown here were shot from dangerous locations and demonstrate dangerous maneuvers such as core punching. It's very fortunate that there weren't additional storm chaser accidents on this event. SLT turned north on the first available paved road, East 550 Road, likely trying to get into the storm's inflow notch, downstream from and northeast of the storm's rear flank core. Playing the notch can afford one of the few views of a possible tornado on a high precipitation supercell, but the maneuver is not without risk. Approaching from the south, the chaser crosses the path of the tornado-producing region of the storm, and then may encounter severe weather once in the notch. The storm was much closer than it was when they stopped east of Overbrook, and getting into the notch without being overrun by the storm would involve a bit of a race at this point. At 5:56 p.m., the velocity couplet associated with the tornado peaked in intensity, approximately 4 miles due west of SLT. Multiple chasers at or near SLT's position reported that the tornado was not visibly apparent at this time. However, chasers with a high-resolution radar display could have recognized a tornado likely existed given the velocity couplet. A minute or two later, SLT's 4 vans drove past storm chaser Quincy Vagel, providing a fix on their location and also a view of the storm structure at this time. Storm relative velocity at this time showed the couplet associated with the tornado less than 3 miles to the west-southwest. The reflectivity indicates this tornado was deep within the ball at the end of the high precipitation supercell's hook and likely completely rain-wrapped. Vagel's position and viewing angle are noted here by the blue arrow, co-located with SLT's position. Knowing the location of the tornado, the chaser, and the chaser's viewing angle, we can plot the location of the tornado here relative to the parent storm structure, even though we can't actually see the tornado. It's just left of due west from Vagel's view. We can see the tornado was buried within the heavy precipitation of the rear flank core, behind a bowing rear flank gust front. This circular region on a high precipitation supercell is heavy rain and hail from the storm's rear flank downdraft, wrapping around the mesocyclone. This region is known by storm chasers as the bear's cage. The wrapping and spiraling rain bands are the bars of the cage. The tornado hidden inside is the bear. It is the most likely location to contain a tornado and is the most dangerous part of the storm. I've circled the approximate size and location of the bear's cage on top of the reflectivity here. You can see there is additional precipitation ahead of the intense core and also trailing it to the south and west in the storm's flanking line. But keep in mind that due to the tilt of the radar beam, the reflectivity is not fully depicting what's happening at ground level. There's lots of precipitation suspended aloft. It's much better to get your bearings using visual storm structure in such a situation. There's other notable structure one can identify here. Ahead of the precipitation core is the storm's updraft base and rear flank gust front, marked in orange. The updraft base wraps around this rear flank core, making a horseshoe shape. Behind this gust front, where the northern end is curling around the mesocyclone, is the most likely location for a significant tornado. To the north is a band of converging inflow marked with a yellow arrow. Like the tail cloud from the previous photo, it feeds into the mesocyclone and the inflow points toward the region containing the tornado. This is typical structure for a high precipitation supercell, and the tornado is located in a pretty much textbook location here. It's imperative that storm chasers recognize and understand this pattern for safety's sake. We'll refer back to this pattern extensively through the remainder of this presentation and look at several additional examples from other analogous storms. Here are the approximate locations of these features on top of the reflectivity and map so that you can get a feel for where they are spatially located. Again, the Lone Star EF2 is located behind the rear flank gust front on the north end where it curls around the storm's mesocyclone. At 5:59 p.m., SLT was northbound and crossed the path of the yet unseen tornado, which was now 2 miles to their west-southwest. Their view of the storm would have included the huge rear flank precipitation core looming to the west and rapidly approaching as it tracks northeast at speeds close to 40 miles per hour. Chasers in the area had been noting an area of radar-indicated broad rotation and higher velocity to the northwest. By 6 p.m., the region was becoming more prominent on radar, while the velocity couplet associated with the ongoing tornado was becoming less defined. Any chasers in the area relying on lower resolution radar displays for situational awareness may have been focused on the area to the northwest, unaware of the danger that existed 1.5 miles to the southwest of the SLT group. We'll take a look at these velocity scans and their meaning later in this presentation. A view to the northwest shows the area in question, what is likely a broad inflow band converging into the northern end of the storm's rear flank precipitation core. By 6:01 p.m., SLT had cleared the path of the tornado, was largely clear of the Bears Cage region surrounding the tornado, and had made it into the storm's inflow notch. However, seemingly unaware of the tornado located in the rear flank core, the decision was made to turn around and head back south to Highway 56. This was the most critical decision-making moment of the chase, as the move put SLT on a direct collision course with the tornado. The SLT vans can be seen here turning around to head south while Quincy Vagel turns east on North 600 Road. Video shared by an SLT client shows a view of the storm at the time of the turnaround maneuver. The group was located on the rim of the rear flank core and Bears Cage region, which was already crossing the road to their south. The dark inflow band extending to the north can be seen converging and curling into the back end of the rear flank core. SLT chasers at this time noted wrapping rain bands to the southwest. Proceeding south, SLT was enveloped by heavy precipitation almost immediately. Chaser Robert Reynolds has a shot of the SLT van southbound before he too turned around at the same location. With Reynolds now southbound, one can see the conditions into which the SLT group was heading. Soon afterwards, Reynolds turned east on North 600 Road, as did Vagel, instead of continuing south like SLT. At approximately 6:03 p.m., the SLT convoy was impacted by the tornado. The tornado was moving northeast at a speed of 40 to 45 miles per hour. According to the damage survey conducted by the Weather Service, the tornado was very close to its peak size and intensity here, with a width of 200 to 300 yards and wind speeds estimated from nearby damage at 115 miles per hour. I'm going to let the following video of the impact play in its entirety. Not to gawk at their mishap, but so that we can understand what it's like to be in such a situation and hopefully learn from it. This is shot from the third van in the line, the third and fourth vans being the ones thrown from the road. However, even though they didn't roll, all four vans were likely subjected to the tornado's winds, as indicated by additional footage from the lead van not shown here, and also the surveyed damage path. Note how difficult the rain-wrapped tornado is to see, and how little visual warning the chasers get that they're about to be struck.
Well, right there. Guys that are trying to get back out to the highway. Okay, let's do that.
Look at that.
Now it's falling here.
Debris falling from the sky. Debris falling here. Tornado right here. Give me the tornado. Stop. Stop.
After the impact, the tornado continued its track to the northeast. Robert Reynolds and crew were eastbound on North 600 Road. Like SLT, they had a similar surprise encounter with the tornado while driving through blinding rain, but were extremely fortunate to avoid being impacted by it.
Well, look at you now, Cody. Where? Yep, you got debris. You got debris. It's right here. It's right here. Back up. Back up. Back up. Back up. Back up. Back up. It's right in front of you. It's right in front of you. It's right in front of you. It just crossed. Yeah, it just crossed right in front of us.
Another tornado developed at approximately 6:06 p.m. over Lone Star Lake, a much larger and more intense tornado that would go on to inflict EF4 damage. There are no clear tornado shots at this time from what I can find. However, from the velocity scans, we can infer that the developing Lawrence EF4 and Lone Star EF2 were likely in progress at the same time. The winds in the rear flank feeding into the developing Lawrence EF4 became so intense they're causing some Doppler velocity aliasing in the scan. The bright green pixels should actually be red outbound winds. The Lone Star EF2 likely became entrained in these winds and its forward speed accelerated. Caught in the larger dominant circulation, the Lone Star tornado may have actually merged into the Lawrence tornado. Such mergers can strengthen a tornado as their energy is basically combined. The Lawrence EF4 expanded and intensified rapidly after this sequence. If such a merger indeed occurred, it was likely entirely rain-wrapped, so we don't have a shot of it. However, a good analog for such a merger is the Pilger, Nebraska storm of June 16, 2014. The dissipating stage of the long-track Pilger EF4 tornado became entrained in the circulation of another developing tornado, the Wakefield EF4. Accelerated by the winds of the larger, dominant circulation, triangulated storm chaser video indicates forward motion of the roping out Pilger tornado was approximately 90 miles per hour. What was once the main tornado of a supercell cycle is now acting as a satellite of the main tornado of the next cycle. The funnel of the rope tornado dissipated, but the remnant circulation likely merged with and helped to intensify the large developing tornado. Alternatively, the Lone Star EF2 may have simply dissipated in close proximity to the Lawrence EF4. An analog for this is the Conger, Minnesota storm of June 17, 2010. The older dissipating tornado from the previous supercell cycle is visible on the left. The developing tornado from the new cycle can be seen on the right. On cyclical supercells, it's not uncommon to have multiple concurrent tornadoes. At 6:18 p.m., the National Weather Service issued a tornado emergency for a confirmed large and destructive tornado. The tornado expanded in size to about a mile in diameter and inflicted EF4 damage on the west side of Linwood, Kansas. Next, we'll take a look at some storm chaser positioning around this tornado. Dalton Cootie was one of the first chasers on the newly developed Lawrence EF4. Approaching the storm from the northeast, looking west from about 2 miles north of the tornado. Strong right to left motion can be seen here, which is the inflow band feeding into the backside of the storm's mesocyclone. Rather than strong left to right motion you would see on the leading edge of a rotating lowering and tornado producing region. This is similar to the structure and part of the storm seen by SLT to their northwest before turning around and heading south. Cootie relocated north for safety's sake. He got a shot at the entirely rain-wrapped Lawrence tornado, surrounding Bears Cage region and inflow band extending north from there. Cootie's position and angle relative to the tornado is shown here, and a wider view showing the tornado heading toward the Lawrence area. The alias green pixels southwest of the tornado likely indicate an intense rear flank downdraft surge that may have been instrumental in the rapid expansion and intensification of this tornado. The reflectivity shows the tornado was embedded in the center of a large comma-shaped circulation, comprising the storm's rear flank. On a classic supercell and if closer to the radar, this would probably look like a more well-defined and typical hook echo. For reference, here's the approximate area of the Bears Cage region, the rain wrapping around the tornado and mesocyclone, the inflow band extending north from there, and the rear flank downdraft feeding into this region from behind. Many storm chasers waited for and caught the Lawrence EF4 from Highway 59 south of Lawrence. The right edge of the funnel can be seen here from Darren Brunen's shot looking southwest from within the storm's inflow notch. Here was Brunen's position relative to the tornado, about 2 miles from the center of the rapidly expanding circulation. From the reflectivity, we can see he's right on the edge of the heavier precipitation in the rear flank core. This precipitation is wrapping around the storm's mesocyclone and the tornado embedded within. The spiraling rain bands from the bars of the Bears Cage hiding the bear inside. Here's that region labeled on the reflectivity, now becoming much larger. The updraft base curls around the rear flank precipitation core, often making a horseshoe, backward C or question mark shape. The tornado is usually on the north or top side of this horseshoe relative to how the storm is oriented. The inflow band runs north or northeast from there. This is the same pattern we saw before with the Lone Star EF2, just larger and more defined. Brunen was north of the center line of the tornado, but was still in the path of the Bears Cage and needed to take his escape route. This was a huge feature spanning several miles. You can see the spiraling rain bands have already crossed Highway 59 to the south, effectively cutting off that escape route. It would be a critical mistake to go south at this point, as this crosses the Bears Cage region and the tornado's path. Brunen correctly took a northbound escape route here toward the storm's forward flank. Several minutes later, this led Bruin into a position northwest of the tornado, coming in behind it as it crossed Highway 10.
Yeah, just south of Lawrence. See the edge of the tornado right up there, cop in front, but that's a big tornado. That's a big tornado. Oh man, big tornado.
You can make out the fat and congealed hook echo of the high precipitation supercell here, the tornado contained in the ball at the end of the hook. The Bears Cage region here may have spanned 3 or more miles at this time, making an approach to and maneuvering around this storm difficult and incredibly dangerous. Darren held here at this position and let the tornado cross. We'll look at different ways to route around this storm at various times at the end of this presentation. First, let's take a look at some radar scans so that we can better understand what may have been happening in the storm and why chasers chose the routes that they did. Considerable attention was put on an area north of the Lone Star EF2 and northwest of SLT's position prior to impact. Chasers identified the area circled in white here as broad rotation associated with the storm's mesocyclone, actively looked for tornadoes in this part of the storm, and took escape routes to avoid it. This large, prominent region may have caused them to overlook the rotation associated with the ongoing tornado to the south, or they simply were unable to see the smaller circulation using lower resolution radar displays and so fixated on the area to the north. This set the stage for a misinterpretation of the radar with potentially disastrous consequences. We look for rotation on Doppler radar velocity scans in areas where the red and green meet, where winds are indicated to be going in opposite directions in close proximity. It's not just about finding bright green next to bright red, however. The orientation of the inbound and outbound winds matters too. If you draw a line between the red and green pixels, it should parallel the radar beam, or point at the location of the radar if you're looking at rotation. The opposing winds flow in a circle around this line. This is a rotation signature, and in this case, the velocity couplet associated with the tornado. If that line were perpendicular to the radar beam or 90 degrees off from what we're seeing here, the opposing winds would be flowing to or away from this line, which is instead a convergence or divergence signature. If we draw a line between the red and green areas to the north, we can see that this line is not fully parallel to the radar beam. It goes off at an angle. Rotation is present here. However, the orientation of this line is important to note because it also indicates significant convergences occurring here. Starting with the formation of the Lawrence EF4, we can step backwards through the previous 30 or so velocity scans and plot the rotation and convergence signatures to see how this storm evolved and the origins of its rotation. Convergence lines are shown here in light blue, transitioning to dark blue as the signature shows more rotation. A couple of patterns emerge here. A, there was a continuous track of rotation from southwest to northeast. You could fit a straight line to this track of rotation really well, and both tornadoes followed this line. And B, before each tornado, there was an area of strong convergence to the north of this rotation track. The convergence became a mix of rotation and convergence, and then focused rotation as it merges with the southwest to northeast track of rotation. The tornadoes develop about the time of these mergers. So what does all of this mean? A is probably the path of the main supercell updraft, or primary mesocyclone. Apart from a few wobbles, it follows a nearly straight line to the northeast like it was on a set of rails. The supercell is also cycling along this line. The regions labeled B are probably inflow surges into the next supercell cycle, likely convergence on an inflow band that is curling into the main supercell updraft and arriving as a focused area of rotation into the primary mesocyclone. As the converging and rotating surge of inflow merges with and gets rooted to the supercell updraft, a significant tornado spins up. Trying to make practical sense of this from a chasing standpoint, there's likely a strong surge of inflow winds meeting a strong surge of rear flank downdraft. These winds are likely revolving around each other, but they're also converging on this line. Stepping through the evolution of these features, we can see intensely converging winds. A well-defined and tight circulation signature does not appear until later, and it occurs on the RFD gust front in fairly close proximity to the existing circulation to the south. By 6:04 p.m., it looks like there were two comparable velocity couplets, and the developing Lawrence EF4 tornado might have been underway at this point. The tornado would have been rain-wrapped and over Lone Star Lake, so its existence probably can't be verified by video or damage survey for this time. It's important to note, however, that these circulations are both occurring deep within the rear flank precipitation core of this supercell. And they're both occurring within the spiraling rain bands of the Bear's Cage. The circulation associated with the developing Lawrence EF4 may have begun right on the top or north edge of this region, the interface between the inflow and rear flank gust front. However, it was likely heavily rain-wrapped and buried in the rear flank core before the tornado even fully formed. The reason it's important to point this out is because both tornadoes occurred within the same structure we see visually on the storm here, that big Bear's Cage region of spiraling rain bands. Check out that large red and green region north of the Lone Star EF2 and SLT's position again. Fixating on that as broad rotation and tracking its center from frame to frame, it looks like the storm has an east-moving mesocyclone, which then makes an abrupt left turn to the northeast. The track line of this apparent circulation is shown in white here. Chasers, including SLT, interpreted this region as the storm's dominant mesocyclone and were actively trying to stay south of its path. However, the reflectivity shows distinct structure that was on a continuous northeast track. At the end of the high precipitation hook, there is a comma head-shaped circulation. The head of the comma probably corresponds to the supercell's main updraft, the tail of the comma to the flanking line updrafts, while an inflow band extends off to the north. The storm maintains this comma head pattern along this northeast track. Both tornadoes appear to be rooted to the center of it, where the comma head curls in on itself. Most important, though, is the physical structure this supercell displayed visually. The circulation of rear flank downdraft wrapping around the mesocyclone was maintained continuously on this straight line track to the northeast. Both tornadoes were associated with this structure. It's important to understand that the Doppler velocity is showing the winds moving in and around the storm, not necessarily where the physical structure or updraft of the tornado producing region is. That region to the north on which chasers were fixated appears to instead be winds converging into and feeding a mesocyclone to the south. Notably, an intense surge of inflow marked in yellow here, and marked in purple a strong rear flank downdraft feeding into the back of the mesocyclone and Bear's Cage region. This is a cyclic supercell, and you're seeing the winds flowing into the next cycle between tornadoes. Think of the storm as a breathing entity. It's taking in a deep breath just before it spins up the Lawrence EF4. Instead of tracking east and then turning north, the storm's main updraft tracked along a continuous northeast line, which both tornadoes followed closely as well. Chasers in SLT's position here, who thought they were south of a mesocyclone, were in reality north of the main tornado-producing region on this storm. The radar can be easy to misinterpret, especially in the heat of the moment and with limited information at hand. So it's crucial that chasers identify visual storm structure, such as the northeast moving Bear's Cage shown here, in order to maintain situational awareness, and not rely on the radar data for their safety. Chasers interpreted this track of strong velocity north of the Lone Star EF2 and SLT's position as the primary mesocyclone. This wound up being a critical mistake, as chasers attempting to stay south of this track instead drove into the path of the ongoing Lone Star tornado. It's important to note that there was rotation in the velocity signature to the north, and it became more focused as it converged into the backside of the supercell's mesocyclone to the south. You can see where the track makes a left turn, which is probably where the circulation on the converging inflow band merged with the northeast moving mesocyclone. The tornado formed at about this location, making a left turn at the start of its track as well. Sometimes big tornadoes exhibit this motion as they first form, starting off as a smaller vortex where the inflow band meets the back rim of the mesocyclone. The developing tornado hooks left around the western and southern rim of the mesocyclone, almost like a satellite vortex, before settling in the center. Once rooted to the main supercell updraft, the developing Lawrence EF4 greatly intensified and was carried off to the northeast. An analogous storm that exhibits this kind of motion on a developing large and violent tornado was the Bowdle, South Dakota supercell of May 22, 2010. We're looking south from within the inflow notch at a storm moving northeast or to the left. You can see a couple of smaller tornadoes here orbiting the parent mesocyclone. The broad rotation of the mesocyclone is visible here, But on the right side of the frame, you can see the right to left motion of the inflow band feeding into the back rim of the mesocyclone. And tornadoes can form on this point of convergence. The tornadoes hook left around the rim of the mesocyclone. Looking west now as the storm moves to the right, you can see the vortices of this large multi-vortex tornado revolving around the rim of the parent circulation. Such behavior is often an indicator that a much larger tornado is forming. These vortices migrate into and collect in the center of the parent circulation, where the much larger tornado develops. Once rooted to the mesocyclone, the tornado takes on the motion of the parent storm updraft, northeast in this case, and it can also greatly intensify. Like the Lawrence tornado, this tornado is also a mile-wide EF4. Spotters and chasers should be looking out for turning tornadoes, and not assuming they will track with the parent storm motion. And likewise, not assume that the tornado indicates the track of the parent tornado-producing region, like the mesocyclone. Look above the tornado at the parent cyclone structure. We just looked at visuals showing fine-scale storm motion. A good way to get a broader approximation of the motion of a storm's tornado-producing region, or the tornado itself, is by using tornado warnings. Encoded within the text of the warning is the initial position and course of the rotation for which the warning is based. This red polygon is the tornado warning valid at the time SLT was impacted by the Lone Star EF2. The warning is shown here with the storm relative velocity at the time the warning was issued. The thin red line in the center marks the initial position and forecast track of the rotation for which the Weather Service is warning for tornadoes. You can see the line starts centered over an area of broad radar indicator rotation associated with the supercell's mesocyclone. This area of rotation gave forecasters several minutes of lead time before the tornado formed to the northeast. Notice how closely the Lone Star EF2 tracks the forecast path encoded in the tornado warning. Even the following Lawrence EF4 closely follows this track. The tornado deviated from the forecast tornado track by less than half a mile. Additionally, there was 20 minutes of lead time from when the warning was issued to SLT being impacted by the tornado. This kind of accuracy and lead time in the forecast tornado track is remarkable. Storm chasers need to take these warnings seriously and not get complacent, even if the warning is for radar indicated rotation and not a confirmed tornado. The high precipitation state of the supercell and the radar beam height likely prevented forecasters from confirming a tornado at the time. For safety's sake, chasers should assume there's a tornado in progress on such a storm, and assume they're approaching the path of a tornado when near the center of a tornado warning. We talked a lot about how the storm that impacted SLT was a high precipitation supercell. We'll spend some time looking at several examples of storm mode, both on the radar and with actual visuals, so that chasers and spotters can get a handle on these supercell types. This is the supercell that produced the Bottle, South Dakota EF4 from May 22, 2010. The same storm we looked at earlier that exhibited that left hooking tornado motion. This was a classic supercell, and the radar presentation of a hook echo is pretty much textbook here. Here are the two main parts of the supercell as seen on Doppler radar reflectivity. The forward flank is a large lobe of precipitation extending off to the northeast. The rear flank is marked by a hook echo, which is the precipitation wrapping around the mesocyclone. Classic supercells are characterized by heavy precipitation in a large forward flank and light to moderate precipitation in the rear flank, which allows for that characteristic hook shape. At the surface, warm moist inflow winds are flowing into the storm from the southeast. Outflow winds fan out from downdrafts in the forward and rear flanks, meeting the inflow winds along gust fronts marked by the blue and purple lines shown here. The inflow winds are channeled into an area of lower reflectivity north of the hook in an area called the Notch. This location was the focus of much of the storm chaser positioning on the Lawrence supercell, so it's important to this discussion to understand what it is and how it works. Storm structure that we heavily focused on in this presentation is labeled on top of this radar scan. Usually south of the Notch, the precipitation in the rear flank and hook of the storm wraps around the mesocyclone and tornado. The streaky, spiraling rain bands on the edge of this region form the bars of the bear's cage. This region is identifiable on the radar as a ball at the end of the hook echo. Running off the back side of this region, over the Notch and into the forward flank, is a thick band of cloud or tail cloud marking inflow into the storm's mesocyclone. It's crucial for chasers and spotters to understand this structure as it provides cues to the location of the tornado, especially in high precipitation storms like the Lawrence supercell, where the tornado is heavily rain-wrapped and not visible. We'll look at several visual examples of storm mode, starting with a classic supercell. Each one of these example storms is warned for tornadoes or produces a tornado. We're looking southwest, downstream from an approaching classic supercell that's moving northeast. You can see heavy precipitation from a downdraft to the right. The storm's updraft and mesocyclone is located on the left. Visually, classic supercells are characterized by heavy precipitation in the forward flank and light to moderate precipitation in the rear flank, which still allows for a view of what's happening under the updraft phase. The relatively clear region between the forward flank downdraft and lowerings in the rear flank is the storm's inflow notch. You can just make out a portion of the storm's updraft base bowing out into a horseshoe shape and a tail cloud feeding into this region. To the northeast, there's low-level rotation as the supercell cycles with a new updraft base. This is not where the tornado develops, however. It forms under the older occluded circulation to the southwest. This is similar to the Lawrence supercell in that the chaser impacting Lone Star tornado was also associated with the older occluded cycle, not the inflow portion of the developing cycle that SLT was trying to avoid to their north. Each storm we'll look at here shows quite a bit of variability in physical structure and presentation on the radar. Viewing angle and position from the previous shots are marked by the blue arrow. You can see a prominent forward flank extending to the north, but also two lobes coming off the storm to the south. The rear lobe on the west side corresponds to the storm's hook. The forward lobe is probably a bowing gust front. Looking west to northwest at a relatively small classic supercell that is moving north, you can see the mesocyclone's rotation evident by the striations in the storm's mid-levels. Heavy precipitation is present off to the north in the forward flank, but really prominent here is the Bear's Cage region, marked by streaky bands of rain wrapping around the mesocyclone. This supercell has a kidney bean shape on the radar, so spotters and chasers might initially expect this storm to be in a high precipitation mode. The radar is a bit misleading here since this is a small low-top storm. The end of the hook and inflow notch are not much wider than the radar beam's width and basically fit within a couple of pixels on this scan. Plus the beam is scanning this storm well above the updraft base. The result is that the radar can't resolve the structure that would suggest a really well-defined classic supercell mode. There's a brief dust swirl tornado beneath a rotating lowering at the start of this time lapse, followed by blasts of outflow as the storm transitions into a high precipitation mode. And then finally lots of churning and roiling motion in the storm's wake. Much larger storm than the previous one and oriented so that the forward flank is pointing southeast instead of north. Notice how fat and congealed the hook looks here, which is common to see with a classic transitioning into a high precipitation mode. Looking west at another large classic supercell as it moves northeast. Multiple surges of wet rear flank downdraft wrap around the mesocyclone as this storm transitions into a high precipitation state. It's common for classic supercells to make this transition as the updraft can no longer support the large amounts of precipitation suspended aloft. Looking northwest, a large EF3 tornado developed within the rear flank core of this storm. Although it's completely rain-wrapped, you can see strong rotation in the clouds aloft and rain bands of the rear flank downdraft. Far from the radar site and transitioning from its classic state, this storm has the bean shape you'd expect of a high precipitation storm. What would be the hook echo on this storm now looks more like a congealed lobe coming off the southern flank. On the other end of the spectrum from high precipitation supercells are low precipitation supercells. On the radar reflectivity, these storms often display no discernible rear flank or hook echo, and the forward flank may appear smaller and weaker than most classic supercells as well. Even though they often have faint returns, it's fortunate for spotters that these storms still display very prominent supercell structure. On the trailing edge of the precipitation core is where you'd find the updraft tower and mesocyclone. The base bows out into that characteristic horseshoe shape, and you often get an inflow band or tail cloud running into the forward flank. Looking west at a low precipitation supercell with wall cloud. Visually, low precipitation supercells are characterized by a translucent forward flank with light to moderate precipitation. The rear flanks of these storms often have no discernible precipitation at all. They look deceptively benign, but the forward flank can contain huge hail, and these storms are still capable of spinning up tornadoes as well. Looking west at a small low precipitation supercell over the Denver airport. This storm was warned for tornadoes, but is now withering away and dying in cool, stable air. In strongly capped environments, it's common for storms to both start off or dissipate in a low precipitation state. Even though there was a twisting barber pole updraft still visible, the storm no longer has much of a presence at all on the radar. We're looking southwest at a supercell with developing tornado. You can see characteristic supercell structure, including the updraft base of the mesocyclone and small tail cloud. Panning from west to south, you can see moderate precipitation in the forward flank and a rear flank that is largely clear of precipitation. Tilting up at the storm's updraft. Tornadoes aren't as common under low precipitation supercells, but they do occur, sometimes appearing as debris clouds without much of any funnel cloud due to the drier air. An example from the archives with a lower resolution scan. You can see the modest forward flank and just a hint of a hook here while this tornado was in progress. It's the high precipitation supercells that chasers and spotters really need to watch out for. These can be some of the largest and most dangerous storms. On the radar, the hook echo is often filled in and the storm takes on a kidney bean appearance, with a kink at the inflow notch. The same supercell pattern is evident here, but the rear flank appears much more fat and bloated. Even the inflow notch may be completely filled in with precipitation. Labeled here are some of the most prominent features chasers and spotters can use to get their bearings on high precipitation supercells, including the May 28 storm that impacted SLT. Identifying structures such as the Bears Cage region and inflow bands is critically important, as this can offer vital clues on where a rain-wrapped tornado may be located that is otherwise completely hidden from view. We're looking south at another tornado-warned storm over the Denver airport, this time a high precipitation supercell. Visually, high precipitation supercells are characterized by heavy precipitation in both the forward and rear flanks. In between, there's often a lighter area or clearing called the notch, and it marks where the storm is drawing in its inflow. The notch on a high precipitation supercell may still contain heavy rain, large damaging hail, and severe winds, however, so it shouldn't be underestimated. Even though the rear flank is socked in with rain and hail, there is still telltale structure on high precipitation supercells that we can use to infer where a tornado is most likely to be. The updraft base bows into a horseshoe, and the end on the side of the inflow notch, where it curls back into the rain, is the most likely location for a main tornado. Inflow bands and tail clouds often point the way to where the storm's updraft is working and where the tornado would be. From a safety standpoint, it's most important for spotters to identify where those spiraling rain bands are wrapping around the mesocyclone, as this is the most dangerous part of the storm. The viewing position for the previous shots is shown here, looking south from along the forward flank into the inflow notch and rear flank. Later on and closer in on this same storm, you could really see the rotation around this storm's mesocyclone. On this broad scale, rotation looks like left to right motion on the leading foreground side, and right to left motion on the back side. It's this left to right motion on the lead edge of the lowering that spotters should be watching for when identifying rotation. Because right to left motion is also associated with inflow bands that are feeding into the storm's mesocyclone and Bears Cage region. It's imperative that spotters and chasers not mistake an inflow band for a wall cloud and the rainy region to the south is only rear flank downdraft. Behind the rear flank gust front and horseshoe-shaped updraft is where that inflow band curls around the mesocyclone and where you're most likely to find the mesocyclone's main tornado. Here's the same region now completely rain-wrapped. A tornado is in progress, but we can't see it. The spotter should be able to infer its most likely location using the available structure, however. It's most critical for chasers and spotters to identify this Bears Cage region, and for safety's sake, not only avoid entering it, but not take escape routes that cross its path. Watch for low-level rotation in approaching lowerings, but when features like this inflow band go overhead, it's crucial that chasers and spotters not panic and flee directly into the Bears Cage region to the south. Looking south at the large hook echo and inflow notch on this storm. A couple minutes later, the tornado is briefly and barely visible, buried within the rear flank core. We're looking south from within the storm's inflow notch. Note the position of the inflow band on the right, the rear flank core marking the Bears Cage, and the position of the tornado. Now compare this scene with the one that SLT had at the time they turned around and went south. Viewed from the same position, in the inflow notch looking south, we see a strikingly similar presentation of storm structure. And the storm chaser impacting Lone Star tornado was located in the same part of the storm as shown in the previous example. It's imperative that chasers identify this pattern and not dismiss this region as merely rainy rear flank downdraft or RFD. We're looking southwest at a tornado-producing high precipitation supercell. In these massive storms, the rear flank precipitation core and Bear's Cage often looks like a large greenish circular region. This region can span several miles in diameter, so it's important that spotters and chasers not just keep their spacing, but maintain a distance of several miles, at least as much as the diameter of the Bear's Cage region, when crossing in front of such storms. A small tornado is visible on the right side here, but this actually turned out to not be the main threat on this storm. You can see that large green core marking the Bear's Cage region and prominent inflow band feeding in from the north. The right edge of something is barely visible here, later identified as a 1.5 mile wide EF3. The small tornado on the right turned out to be a satellite, arriving on a circulation where the inflow band converges into the back rim of the mesocyclone. The horseshoe-shaped updraft base and inflow band pointing the way can offer clues as to where the tornadoes may be on this storm. This sequence is a good example of the dangers that can exist with a high precipitation supercell, but also the dangers of chasers becoming fixated on a single threat. Chasers focused on the smaller, more visible satellite tornado may overlook even larger dangers that still lurk inside the Bear's Cage. Chasers should assume that any rain-wrapped portion of the Bear's Cage region on a high precipitation supercell contains a tornado, even if another tornado is already in progress. The most diligent chasers may elect to treat this entire region as if it is the tornado itself, by not only keeping a wide berth, but also by maintaining safe escape routes that do not cross its path. Another commercial storm chasing tour operating under the rear flank of this storm had a van that was impacted and damaged by irrigation equipment caught in severe winds. We're looking southwest from within the notch of this massive high precipitation supercell. Supercells come in a wide array of shapes, sizes, and configurations. Here are several storms spanning much of the supercell spectrum, plotted here to scale so that you can compare their sizes and orientations. The size and visibility of the Bear's Cage region varies tremendously on these storms. From an area barely a mile across on the December 1, 2018 storm to over 5 miles across on giant high precipitation storms like the ones that produced the Lawrence EF4 and Joplin EF5. The Bear's Cage region is completely socked in with heavy rain on these storms, but on a classic like the Bowdle, South Dakota storm, there may still be good visibility under the rear flank of the storm. And the spiraling rain bands that define the Bear's Cage region may be entirely absent on low precipitation supercells like the Thackerville, Oklahoma storm. Hopefully chasers and spotters can see a reflectivity scan like this and anticipate what kind of storm they're dealing with, what structure to expect, and what steps to take to stay safe. Initially looking for supercell features like the hook echo of the curling rear flank and the forward flank extending off to the northeast. And using this to anticipate where structure should be, like the Bear's Cage region, inflow band, and the notch. All great visual cues that chasers and spotters can use to get their bearings on such storms. Doppler radar is a major part of effective storm chasing. It has numerous shortcomings, however. The data is often coarse, significantly delayed, and the beam may be scanning thousands of feet above the ground, missing small features in the lower levels, including tornadoes. Because of these limitations, chasers and spotters should not rely on radar data for their safety. This is the Level 3 storm relative velocity as shown on the Gibson Ridge GR Level 3 software during the time of the Lone Star EF2. This is the same software and data that some of the SLT staff were using during their May 28 chase. Shown here about 10 minutes before they were impacted, the velocity couplet associated with the tornado is visible here and can be seen about 4 miles due east of Overbrook, right on Highway 56 and in the center of the tornado warning polygon. Such a feature would be easy for chasers to miss, and a tornado probably couldn't be confirmed with this radar data alone. Instead of using the radar to stay safe, chasers should maintain their situational awareness using visual storm structure. I can't emphasize this enough. Chasing in the core of a supercell, totally blind except for the occasional radar scan, is extremely dangerous and can lead to injury and death. Here are a few more examples to emphasize the importance of visual structure identification. You can see the massive bear that is a mile-wide EF3 becoming rain-wrapped in the Bear's Cage. Chasers should be watching for streaky rain bands that are spiraling around the mesocyclone. A 1.5 mile wide EF4 lurks in the Bear's Cage of this storm. On a high precipitation supercell, the Bear's cage often looks like a large green circular core of precipitation. To the north of this precipitation core, strong right to left motion indicates a thick inflow band feeding into the mesocyclone. Chasers holding a position in the notch of a supercell should not take southbound escape routes that cross the path of the Bear's cage, which is exactly what I'm doing in this clip. This is an extremely dangerous maneuver. Losing this race can result in injury or death. Most chasers are learning the hard way through risky trial and error. A primary goal of this presentation is to provide examples of the errors so that chasers don't have to repeat these mistakes themselves. I'm happy to share my own past close calls and mishaps from which I've learned. This sequence is a good analog for the tornado positions and supercell cycling that we see on the Lone Star and Lawrence storm, except without the heavy rain wrapping. You can see a tornado in progress on the left, associated with an older occluded cycle of the mesocyclone. The tornado occurred well behind the bowing rear flank gust front seen in the foreground. The supercell is cycling downstream to the north-northeast with what looks like a robust wall cloud and thick inflow band. Low-level rotation is present on this northern feature, where this lowering curls into the rear flank core of the storm. Chasers should anticipate a tornado from the next cycle associated with this circulation, while not losing sight of the other threats, possible tornadoes, and the overall picture of this storm. On a high precipitation supercell, this entire region would be filled in with rain and hail. I've drawn over the image so that you can visualize this. Even though we can no longer see the tornado, there are still cues in the supercell structure to help us get our bearings, including a horseshoe-shaped updraft base and inflow band feeding in from the north. Using this structure, we can infer where a tornado would most likely be, behind this horseshoe-shaped base where it curls on the northern end. Take a look again at our high precipitation version of this storm and where the tornado is in relation to the updraft base, rear flank gust front, and inflow band off to the north. Now compare this to the structure from the May 28th storm as it's producing the Lone Star EF2 that impacted SLT. The storms not only look eerily similar, but the tornadoes are in the same general location on the storm, behind the apex of the bowing rear flank gust front and in the reign of the rear flank precipitation core, south of the inflow region to the north. This is not a coincidence, but a basic supercell pattern that all chasers and spotters should be aware of. This was a cyclical supercell. While the tornado from the old occluded circulation is roping out, the storm is cycling with a new circulation to the north. This is another reason why this storm is a good analog for the storm that produced the Lone Star EF2 and Lawrence EF4. The Lawrence supercell cycled in a very similar configuration, and chasers in the area claimed it was the developing circulation to the north that they were maneuvering to avoid. Looking at the parent supercell structure, however, you can see that the developing circulation is already becoming occluded behind the rear flank gust front, and the next tornado hasn't even developed yet. On a high precipitation supercell, this entire bowing gust front would be swamped with rain, and the developing circulation to the north would likely already be entirely rain wrapped before the tornado even formed. This is what happened with the May 28 supercell with the Lawrence EF4 that followed the Lone Star EF2, developing within the same rain-wrapped Bear's Cage region. Chasers and spotters do need to be aware that it's typical for supercells to cycle in the clear air inflow notch downstream from the rear flank core and established Bear's Cage region. Maintain your situational awareness by keeping your head on a swivel and looking for low-level rotation and additional lowerings. There's a developing tornado on the left side of the frame here. It's important to not become fixated on one thing like the tornado in the background. Please see the video clip Understanding How Supercells Cycle for a conceptual overview of this process. It needs to be pointed out that tornadoes are indeed possible on the inflow band region north of the mesocyclone as well. The notch is not a region free from dangers. You can see a small rope satellite tornado develop here on the inflow band to the right of the mesocyclone's main tornado. Circulations in the form of vertical vorticity are feeding into the mesocyclone along these inflow bands, and these circulations can spin up into tornadoes before they become rooted to the mesocyclone. I looked for structure with tight low-level rotation in the area cited by chasers to the north of the Lone Star EF2. Motion was difficult to discern due to the contrast and clarity, and I wasn't able to identify tornadic rotation in this location at this time. If present, it was probably broad-scale rotation as the inflow band curled into the rear flank core to the south. The area to the right in this frame appears to be mainly converging inflow band feeding into the Bear's Cage region to the left. Even if there was low-level rotation present in the storm structure shown here, SLT chose to avoid a portion of the storm that visibly contained no tornado, and instead chose to enter a portion of the storm without visibility, a region which can and often does contain a tornado. This was a critical mistake. It was this rainy region to the south of SLT and the storm's inflow notch that harbored both the Lone Star EF2 and Lawrence EF4 tornadoes. This is the most dangerous part of the storm. For a more in-depth presentation on visual structure identification, please see the video Storm Spotting Secrets. The threat of a single tornado lurking within the bear's cage is not the only danger of which chasers need to be wary. Multiple potentially life-threatening hazards are contained within the rear flank of a supercell. It's possible for multiple significant tornadoes to exist concurrently in the bear's cage from different cycles of the supercell. And 2 concurrent tornadoes likely occurred in the bear's cage of the Lawrence supercell minutes after SLT was impacted. An array of satellite circulations is also possible, both close in to the main tornado beneath the immediate parent structure such as the tornado cyclone or wall cloud, and also further out, orbiting the rim of the large-scale mesocyclone, potentially miles away from the main tornado. Tornadoes are even possible embedded within the straight-line wind surge of the rear flank downdraft, well south of the main tornado. Looking south, a small rogue tornado crosses the road here, carried by rear flank downdraft winds, while a large wedge tornado behind the chaser moves away a couple miles to the northeast. In a high precipitation supercell with limited visibility, it might be impossible to negotiate fast-moving satellites with enough time to avoid them. Severe straight-line winds of hurricane force are common in the rear flank of high precipitation supercells, as well as large damaging hail. Even general road hazards can be some of the most dangerous. Watch out for disoriented animals and people, debris and water in the road. Worst of all, once in the core of a high precipitation supercell, chasers may suffer a complete loss of situational awareness. This is an extremely dangerous situation. Without visual structure on which a chaser can get their bearings, the dangers lurking ahead are unknown. This is the scenario in which SLT found themselves in the minute before impact, driving through blinding rain and unaware that they were heading into the path of an oncoming tornado. It's imperative that chasers maintain safe escape routes in order to avoid falling into the bear's cage and resulting loss of situational awareness. In this next section, we'll take a look at the route options that SLT and other nearby chasers had while navigating around the Lawrence supercell, the amount of danger associated with each, and some safer alternatives. We'll focus on several key moments in SLT's chase here. The radar is shown for illustrative purposes, but again, it's imperative that chasers make crucial route planning decisions using visual storm structure, and not just radar. At 5:55 p.m., SLT was eastbound on Highway 56. Their view to the west would show low contrast supercell structure, including an inflow band to the north of an updraft base wrapping around the Boeing rear flank core. The chaser should have a handle on the bear's cage region behind them. I've colored it completely opaque here as the presence of a tornado is unknown. However, safety-conscious chasers should assume the bear's cage contains a tornado on a tornado-warned high-precipitation supercell like this one. Chasers should also factor into their route planning that this region spans at least a couple miles in diameter and is tracking rapidly to the northeast. A rough approximation of the path of the bear's cage is shown shaded on the map here. We'll use colored arrows to compare different route options. The darker the color, the more dangerous the option. The safest option for SLT at this point in the chase would be to keep going east down Highway 56 and gain more spacing from this large, fast-moving high-precipitation supercell. In fact, this is what most chasers did, heading to the major north-south Highway 59 before intercepting the storm south of Lawrence. A riskier move would be to turn left onto the paved north option and make for the storm's inflow notch. This option may offer one of the few viewing locations for a tornado on such a storm, but it's a dangerous maneuver because it crosses the path of the tornado-producing region of the storm. The chaser needs to travel several miles to make it into the notch and clear the bear's cage. They should make sure they have at least this amount of spacing east of the storm before attempting this maneuver. With the rear flank core just a couple miles behind them and moving northeast at 35 miles per hour, it would be a race at this point to clear that distance. SLT made the left turn, a visual looking north at what lies ahead on the riskier north option. You can make out the low contrast forward flank precipitation core of the supercell. Northbound for a couple miles, this would be SLT's view to the west. Chasers should note that they are almost even with the apex of the Boeing rear flank core and that it is rapidly approaching. Keep checking to see where the storm is and which way it's moving. Don't assume it's going to hold the same course and be where you expect it to be after the last time you checked. If there's any question about not being able to make it across the path of the bear's cage without being impacted, this would be the time to abort such a maneuver. If it looks like you might be impacted by the storm's core, turn around before you cross the storm's apparent path or before you've crossed the apex of that Boeing gust front. Turning around at this point, SLT may still have been clipped by the rear flank core and associated severe weather, but would have avoided an impact with the tornado. The much riskier option would be to continue racing the rear flank downdraft core and bear's cage region. Once across the path of the bear's cage and past the apex of the Boeing gust front, there would no longer be enough time to turn around in this case. With no immediate east option, the chaser must commit to getting into the storm's inflow notch to the north. It's common for there to be severe weather in the notch, including large damaging hail and severe winds. Chasers electing to take on such positions are also electing to lose glass and damage their vehicles. Chasers should be prepared for this in order to avoid an impact with a tornado in the bear's cage. SLT successfully made it into the storm's inflow notch without incident, managing to clear the path of the tornado and the bulk of the bear's cage region. From SLT's position, the bear's cage region can be seen here, crossing the road to the south. SLT's position shown here relative to the bear's cage region. You can see they were positioned right under the northern rim of the horseshoe updraft. Had SLT continued north, they would have cleared the bear's cage and any rain-wrapped tornadoes contained within it. This was their safest option at this point, but the maneuver is not without risk. Large damaging hail and severe winds are common in this part of the storm, or even a future tornado if the next supercell cycle is displaced to the north of the previous cycle's track. The worst possible and most dangerous option at this point would be to turn around and head back south. This route crosses the entire span of the bear's cage region and puts the chaser in danger of being impacted by a rain-wrapped tornado. Almost equally dangerous, and for the same reasons, would be to turn east at this point. Again, this route crosses the path of the northeast moving bear's cage region and potentially any rain-wrapped tornadoes. Additionally, this route uses a lesser road on the grid that degrades to gravel. Using unpaved roads in the core of a high precipitation supercell is extremely hazardous. Several chasers took this route and were very fortunate to miss an impact with the rain-wrapped tornado. A couple minutes later, a view of both the south and east options shows them completely enveloped by the bear's cage and rear flank core of the supercell. We'll take a look at some route planning around the following Lawrence EF4 tornado as well. Here is Darren Brunen's position relative to the Lawrence tornado and surrounding bear's cage region. His view to the southwest from within the notch, looking at the entirety of the bear's cage region. The tornado itself is partially visible here, but compare this view to the one SLT had as they turned around. The position and angle is quite similar, with Brunen on the northern rim of the horseshoe updraft as the bear's cage region crosses the road to the south. As we saw before, a south route at this point would be extremely dangerous, as it requires a core punch through the bear's cage and crosses the path of a tornado. It seems kind of obvious not to do this when looking at the map here, but chasers have this gut urge or knee-jerk reaction to flee south when escaping storms. Once in the notch, southbound escape routes cross the path of or send the chaser directly into the most dangerous part of the storm. Many have gotten away with this on smaller, slower-moving supercells or escaped with just a near miss. These giant, fast-moving, high-precipitation supercells are far less forgiving, however. The tornado on this storm was approaching a mile in diameter at this point, and the bear's cage region, with all of its associated hazards, was at least 4 miles in diameter. Chasers should allow several miles of spacing when maneuvering in front of large, high-precipitation supercells. Many chasers elect to simply not chase these types of storms at all. After carefully considering his position and the path of the storm, Brunen correctly took a north escape route toward the forward flank of this storm. Again, severe weather is common on such a route, but the inflow notch on this supercell had enough visibility that Brunen could retain situational awareness by sighting storm structure. Heading north put Brunen behind the tornado in the region of the storm where the inflow notch feeds into the hook. Looking east, you can see the tornado to the right and the spiraling rain bands of the bear's cage wrapping around it. Chasers should take a few moments to note the apparent motion of the storm and tornado. in this case to the left and away. The tornado is moving northeast. Once behind the tornado and bear's cage, it's imperative that chasers not attempt to race east to regain their position ahead of the storm. Much like heading south in the previous scenario, this route crosses the path of a tornado and leads to an impact with the bear's cage and the hazards associated with the rear flank core. The clear air up ahead may look safe, but chasers are perilously racing a freight train when they take escape routes that cross the tornado's path. Brunin held his position here and let the tornado cross ahead of him. Chasers who need to take an escape route from this position, perhaps due to severe weather or a loss of visibility, should consider a westbound escape route through the back side of the hook. Severe weather is likely in this part of the storm, but again, storm chasers are electing to encounter damaging hail and wind when taking on positions from within the notch. For additional information on escape route planning, please see the video Safety Lessons from El Reno. It turns out it's quite hard to get hit by a tornado. You have to be in just the wrong place at just the wrong time. Even driving blind straight through the bear's cage, your chances of being impacted by a tornado are quite low. Diligent and safety-conscious chasers make mistakes and have their close calls. The rare times that they fall into the bear's cage, they're likely to emerge without incident. But chasers who routinely find themselves in such a position are playing a game of Russian roulette. The chances of a tornado impact are low on any given bear's cage core punch, which may lead to complacency, unnecessary and reckless risk-taking, and unwittingly dangerous escape routes. But if those low probabilities are realized, the results can be catastrophic. To promote storm chaser safety, we need to recognize patterns of dangerous behavior, or else chasers will continue to repeatedly make the same mistakes. And these are the chasers most at risk of having a disastrous encounter. On May 22, 2011, SLT had a close call with an EF5 tornado that devastated Joplin, Missouri. This tornado directly killed 158 people. Video of their encounter can be viewed on YouTube. Overlaid on top of this map of the tornado's damage path is SLT's position at the start of the video, indicated by the black dot, and their course during the video as they're escaping the tornado. The context and situation that put SLT into this position is different than that of the Lone Star, Kansas event of May 28, 2019. However, these two incidents have many striking similarities. Both storms were similarly sized high precipitation supercells. Both storms produced mile-wide violent tornadoes. In both events, SLT started north of the tornado's path and took a southbound route that crossed the tornado's path. The southbound route crossed the entire span of the ball at the end of the Hook, Echo, and Bear's Cage region in both the Joplin and Lone Star events. In both events, the tornado had been in progress for several minutes and traveled several miles before SLT started heading south. In both events, SLT's starting position had already been warned for tornadoes by the National Weather Service for approximately 20 minutes. Had SLT instead been impacted by the Joplin EF5 or the Lawrence EF4, everyone in the group could have easily been killed. Vehicles are death traps in violent tornadoes. This incident triggered a large emergency response and recovery effort involving numerous personnel and vehicles. It's the duty of first responders to help others, even at the cost of their own safety. The least we can do in return as chasers is act responsibly out in the field by not taking wholly unnecessary risks and engaging in reckless behavior that could put other people in harm's way. First responders may have to drive through dangerous conditions to reach you, and these first responders may then be needed downstream to assist residents caught in an unfolding disaster. The small communities of the plains have limited resources, and when accidents like this happen, these resources have to be diverted to storm chasers who should know better. The tornado impact and injuries near Lone Star, Kansas were entirely avoidable. Using visual structure identification, chasers can locate dangerous parts of the storm, such as the Bear's Cage. With diligent escape route planning, chasers can avoid any potential tornadoes contained within these parts. Escape routes should be taken as soon as chasers realize that they're in the path of a tornado or tornado-producing region. Escape routes should be taken before a dangerous loss of situational awareness occurs, such as when visuals are lost in the precipitation core or if the chaser is unsure of the storm's current state. And finally, the escape route should never cross the path of a tornado or tornado-producing region. Adherence to these safety practices would have likely prevented this incident. A contributing factor to this incident seems to be an over-reliance on and misinterpretation of radar data. The danger of the situation was compounded by the high precipitation state of the supercell and close proximity at which chasers were operating. This was not simply a case of getting too close, however. Numerous other chasers were operating within a couple miles of the Lawrence EF4 while maintaining situational awareness and routes that did not cross its path. Instead, critical errors were made that put SLT on a collision course with a significant tornado. A southbound route was chosen that led to a direct core punch of the Bear's Cage, a region that should have been readily identifiable by chasers. This was followed by a loss of situational awareness that resulted in a tornado impact with injuries. Unfortunately, these are some of the same lessons we should have learned and relearned after El Reno. The sad truth is that as long as chasers continue to chase in the Bear's Cage while picking bad escape routes, future injuries and deaths will be inevitable. That big green core of the Bear's Cage is a freight train coming down the tracks. We don't tell people to drive big trucks and wear helmets so that they can survive train impacts, or drive faster cars so that they can beat trains at the crossing. Just like with violent tornadoes, it doesn't matter what you're driving. If you get hit by that train, you could be killed. Stay off the tracks and don't race across them when the crossing guards are coming down.